Alright, so today we'll talk about 4.8, the antiderivatives, okay? So as you can see, I got my whiteboard, so it's very good. So later on, I'll start to use this whiteboard to do the regular lectures and also the examples, okay? So exciting, okay. Um, and the definition says like this. We have a function capital F. This capital F is called an antiderivative of small f on an interval if we take the derivative of capital F, that gives us a small f, okay, for all x in this interval, okay, for all s in this interval. All right, so that's the definition, but now let's look at some examples and let's think about it. Before, from chapter 2, 3, and 4, we all talked about we give you a function, ask you to figure out, okay, what is the derivative of those functions, and we learned, the constant multiple rule, and then the product rule, the quotient rule, and also the chain rule, right? And also about the derivative of the logarithmic and the derivative of the exponential, right? E to the power of something. And, so that's the derivative part. But starting from 4.8, we're starting to think about it the reversely. Okay, the question is like this, okay? If I have a function, let's say fx equals 2x, all right? And then which function, that is the capital Fx, such that when you take the derivative of this part, it gives you 2x. Well, if you think about it this, do you agree x squared works, right? Because if you take the derivative of x squared, that'll give you 2x. That is exactly the definition, right? The antiderivative of f, which is x squared. But is capital Fx is x squared is the only antiderivative? Maybe not. Why? Let's do this. Do you all agree that if I plot at a constant number 1 and we take the derivative of this, do you see that it still goes back to 2x? So x squared plus 1 is also an antiderivative of f. Okay. Now, what about, I don't know, so if I alternate those arbitrary numbers to 100, so the derivative of x squared plus 100, do you see that it still gives you 2x? Does that give you some ideas? In fact, you can see that, guys, the antiderivative, you have infinite many antiderivative functions that fit well to this function fx equals 2x, right? As long as the format is x squared plus 1 arbitrary constant, right? Because any arbitrary constant, if you take the derivative, it's going to become into 0, okay? So under this situation, this is the notation here. We're starting to introduce what we call an arbitrary constant c, okay? Let this c denote arbitrary constant, okay? So this is what we call the general antiderivative, okay? For the fx equals 2x, again, plus a constant c. Now, if you're comfortable with this, let's think about the next one. If fx is equal to sine of x, what is the general antiderivative function for fx? In other words, which function, when we take the derivative, it gives us is sine of x. And we learned that if you take the derivative of cosine x, it gives you is negative sine of x, right? So we're pretty close. We know that the derivative of cosine is negative sine. But how do we get sine of x? Okay. Now, Let's think about this. You will see that if you put a negative sign in front of cosine x, that will complete the task. Because if you take the derivative of this part, it will give you sine x. And also, don't forget plus the arbitrary constant. Okay. And last example, let's look at this one. Fx is equal to e to the power of 2x. Okay, e to the power of 2x. And then, you see when we learn the exponential functions derivative part, we know that the derivative of e to the power of x is e to the power of x, right? And e to the power, what is the derivative of e to the power of 2x, guys? Let's think about it for maybe 3 seconds. Okay, so 1, 2, 3. So the derivative of e to the power of 2x, based on the chain rule, is going to be e to the power of 2x multiply the derivative of the inside function, which is 2. So give us is 2 times e to the power of 2x, right? This is fairly close. But what we need is we're looking for a function. If you take the derivative, that is going to give us exactly e to the power of 2x. So let's do some small modification here. As you can see that if you take the derivative of e to the power of 2x, that gives you 2 e to the power of 2x. What if we multiply 1 over 2? Do you see that when you take the derivative of this part, it exactly go back to here, right? So, and always don't forget this arbitrary constant c. Okay, so that's about some basic examples. What is the antiderivative? Now, in our textbook, they give you a formula sheet about the antiderivative. There are a lot, but I wrote some on the other side. Fancy, right? So let's see. 1, 2, 3, 4, 5. So those 5 antiderivative formulas, you have to know them. Okay, guys. They're gonna be in our test. Okay. Of course, there are more formulas there, but those 5 are the most important and fundamental ones so far. Okay, so let's go over with this one. If we have fx is x to the power of n, let's say x squared, then the general antiderivatives, it follows this format. X to the power of n plus 1 over n plus 1 plus a constant c. And of course, this n cannot be negative 1. What does this mean? For example, if you think about it, x squared, okay? So let's look at this example. If you have x squared here, then the general antiderivative n equals 2, it's going to be x to the power of 2 plus 1 over 2 plus 1. And you will see that it's x cubed over 3. And if you take the derivative of x cubed over 3, do you see that it goes back to x squared, right? And of course, don't forget to plus this arbitrary constant. Okay, so that's one small example. And if the function is e to the power of kx, then the general antiderivative is 1 over k times e to the power of kx plus c. We just talked about that example, right? Remember that. E to the power of 2x, then the antiderivative is going to be k equals 2 in our problem. It's 1 over 2 e to the power of 2x plus c. Okay? So that's our solution here. So let me circle this part. Okay, so this is example. This is example. All right. The other one, sine of k of x, and then the general antiderivative is negative 1 over k times cosine of kx plus c. Let's look at another example here. For example, if we have, I don't know, so sine of, let's see, 3x. Okay? And in our problem k equals 3, so follow this formula. We're going to have is negative 1 over 3 cosine of 3x plus constant c. Okay? And, all right, so next one, cosine of kx, then the antiderivative is 1 over k times sine of kx plus c. And for example, what if we have cosine of 2x? Okay. Then the antiderivative is going to be 1 over 2 sine of 2x plus n. Partial constant. Okay. And last one, 1 over x, the antiderivative is going to be ln of absolute value of x plus constant c. And again, x, it can be positive, it can be negative, but either way it will work. Okay, so those are the 5 antiderivative formulas. And also, guys, the good thing for this antiderivative process is you can always check your answer, right? Because we already know very well about the derivatives. So when you get an answer, take the derivative of your answer, try to see if it matches with the given function. If it is, sure, this is the correct answer. If no, you have to rethink about it. There's something wrong. Also, never forget about this constant c, okay? Because it stands for a general antiderivatives. And also, this is called the family solutions, because this C, it's arbitrary, so it stands for a family of solution. Okay, so I'll stop here and then see you guys later.